Welcome to Magnetized Labs. We are back with a new video. Today we are going to see the design of USB 3.1 Generation 1 Superspeed Industrial Smart Hub using USB5734 IC. The board will look like this after the PCB design. I am going to explain how to design this USB hub from the start. What is USB hub? A USB hub is an electronic device which allows user to connect multiple USB devices simultaneously. For example, if you want to connect two cameras and two USB pen drives and two USB sound cards, you definitely need a USB hub. This is where it will help. So what is the difference between USB 2.0 and USB 3.0? Exactly, the speed itself. USB 2.0 has three different speed modes: low speed, full speed and high speed. Low speed will work up to 1.2 Mbps, full speed will work up to 12 Mbps, high speed will work up to 480 Mbps. When it comes to USB 3.0, it can give the speed up to 4800 MP per second. Also, this has a super speed mode. This is the block diagram of our project. I have used USB 3.1 Superspeed Smart Hub controller, which is USB 5734. It is capable of giving 4 downstream ports. I have added current limit protection for each downstream ports with a load switch IC, and I have given a DC jack to supply external power to the downstream ports. And then I have given a port speed indicator LEDs, which is used to denote a particular port whether it is operating USB 2.0 interface or USB 3.0 interface. And then I have used Type-C connector as an upstream port, which is universal nowadays. And then I have used two LDO circuits, which is used to convert from 5 volt to 1.2 volt and 3.3 volt to supply USB hub controller IC. And let's go to the schematic now. Yeah, this is the schematic. This is the Type-C connector, which is upstream connector, and as we all know, RX plus and RX minus, TX plus and TS minus connections are for USB 3.0 interface, and D plus and D minus signals are for USB 2.0 interface. And then V bus 5 volt node is to power the USB hub device. And then this is the CC pin, channel configuration pin in Type-C connector. I have used this pin to just get the power from the host device, so I have connected this pin to ground through 5.1 kilo ohm resistor. This is the LDO for converting the voltage to 3v3 from the 5 volt from the USB host Type-C connector, and I have used necessary decoupling capacitors, and same goes for 1.2 volt as well. These are the port indicator LEDs, which is used to denote the speed of the each and individual port as well as the host port. In this, like, if the blue LED is blinking, then port 1 is operating at USB 3.0 interface. If the yellow LED is blinking, then the port 1 is operating at USB 2.0 interface. This is the DC jack for external supply to all the downstream port connectors with decoupling capacitors. These are all the load switches which I have used for each and individual port. Whenever there is a failure of power or short circuit at the downstream port, this particular load switch will isolate that failure part of it. I have configured each load switch for 2.25 amps, and then reset switch, which I have used for manually resetting the USB hub whenever there is a need. I have used the LED in parallel. Whenever there is a normal operation of USB hub, this LED will be on. Whenever there is a reset state, this LED will be in off condition. We'll go to the USB 5734 hub controller connections. This is the V bus deduction pin, which is used to deduct the main V bus. This is operating at 3.3 volt level. We have to give more than 0.7 volt to make this pin as high. I have used potential divider of two numbers of 100k resistors, and then which will result in 2.5 volt. These are all USB 3.0 and USB 2.0 upstream port connections, and this is the reset pin. I have pulled it to 3v3 using 1k resistor, and this pin is also connected to the LED. This is R bias pin, which is used for setting the internal bias in the hub controller IC. I have used 12k resistor to pull it down to ground as per the datasheet recommendations. This is a test pin, This is an analog test pin which is also have to be grounded using a 1K resistor. This is the crystal oscillator circuit. I have used 25 MHz crystal, 16 picofarad load capacitors. This part of the circuit should be taken care while routing because this is operating at very high frequency. This hub controller has several communication interfaces such as SPI, UART and I2C. I am not using any kind of communications here in this USB hub. I am just using this as a USB hub, and there are several features such as battery charger enable and configuring the non-removable ports and all. So I am not using the battery charging. I have used a 200K pull down resistor to disable the battery charging, and then configuring of non-removable ports. For that I have configured all the ports are removable. So I have used 200K pull down resistor and then configure strap pin. This pin is used for configuring the USB hub controller in several modes. There are several modes of operation in this USB hub controller. One is mixed mode, other one is flux connect mode, then speed indicator mode, GPIO mode, battery charging or power delivery indicator mode, full UART mode. I am using this pin for speed indicator modes. So I have just used 10K pull down here in this pin. This program function pins I have used for port speed indicator modes. This is 3v3 power supply for the hub controller, and then same goes for 1.2 volt. These four pins are used to control the each and individual downstream ports. I have connected these four pins to the enable pins of the load switch for the each downstream ports. These are all the USB 2.0 and 3.0 connections for all the four downstream port connections. This shield I have connected to ground through 330 ohm resistors and 0.1 microfarad capacitor for better signal integrity and reduced noise. These are all mounting holes and decoupling capacitors for each port supply. We'll go to the PCB now. Before designing the PCB, it is very important to design the stackup of the PCB. When it comes to the stackup, I have used a 6-layer stackup for easier routing and convenience of the layout. First layer I have used to route the differential signals of the USB with ground, and the immediate layer of the first layer is the second layer I have used as the return path and a reference for the paths for the signals. The third layer I have used for 1.2 volt power supply because there are many pins in the USB hub controller which is using 1.2 volt as a power supply. I have used this third layer for 1.2 volt, and for this third layer, the second layer is the immediate reference and return path. And fourth layer I have used for external 5 volt, and the sixth layer I have used for ground and some differential signal routings. And for both fourth and sixth layer, I have used fifth layer as the reference and return path. In PCB, so this is the USBTypeC host connector. From this, the 5 volt is coming to the LDO to convert to 3v3 and 1.2 as well, and both are used to supply the USB hub controller. And then this is the reset switch which is connected to the USB hub controller, and then VBus detection peripherals, and this is the crystal oscillator circuit which is routed in a very short length to avoid the interference. And then these are all the downstream port. For each downstream port we have a load switch IC to prevent the power failure or any other short circuit protections. These are all the port speed indicator LEDs. For all the USB TX plus and TX minus, RX plus, RX minus, data plus and data minus signals, I have used differential routing to avoid reflections and noise and signal integrity problems. I have used 90 ohm impedance matching for this USB differential lines because this is a very high speed design. When it comes to high speed digital designs, we actually have to take care of the PCB layout and stackup as well as the routing, because when it comes to the USB of this project, this is operating at very high speed up to 5 gigabits per second. There is a chance of noise and EMI EMC interference. So to mitigate all of these things, we have to stitch the plane with the ground vias to couple to the proper reference. This is the 3D view. So this is the upstream connector and downstream connectors, and then in the middle USB hub controller. This is the reset switch crystal oscillator circuit and load capacitors, and their minimum peripherals of the hub controller IC. These are all port speed indicator LEDs, and then LDOs for the power supply of the hub controller with decoupling capacitors, and load switches for each and individual downstream ports. I have kept a few capacitors and resistors at the bottom side. We'll go to the Stackup now. Yeah, this is the 6-layer PCB. Each layer consists of 35 microns and standard FR4 layer with 1.6 millimeter thickness, rectangular size 80 cross 75 mm, silk screen as usual white for the top and bottom, solder mask green color for the top and bottom, and then temperature gradient more than 170 degrees Celsius. I do always prefer impedance control. Yes, this is up to you. Finish, unique finish, and then here it comes the very important part, impedance control details. First layer I have used for differential routing, and then second layer I have used as a reference. Same goes for sixth layer as the differential routing, and fifth layer as the immediate reference and return path. I have used 90 ohm impedance matching, and then trace width and trace to trace gap is depend on your manufacturer. When it comes to the application of USB hub, you can use that USB hub as a standalone circuit, and you can see the USB hub circuits in your laptop docks, PC motherboards, and modern PC monitors, multifunction USB 3.1 Generation 1 peripherals, and it comes in advanced televisions, high-speed embedded circuits. So I hope this project will help you a lot in designing the high-speed digital design PCB circuits. If you have any suggestions or comments, please let us know in the comments. I will attach the schematic and BOM in the description. Thank you so much.